Why are you so excited?
Because we're going to learn about the touchdown function. Y equals x squared. Touchdown! Back in the old days, when football players went across the line, they said, Y equals x squared! Yay!
It's completely correct. Let's get to it. Let's do this exercise. Here, as Slopey wanted, we're going to consider f of x equals x squared, the touchdown function. And really on the interval negative pi to pi. So the first question is, show the Fourier series is this expression. So I thought, well, we just need to calculate the coefficients. So f of x is going to be some coefficient times the first guy plus some coefficient times cosine of kx over square root of pi from k greater than equal to 1, and then plus sum over n greater than equal to 1 of bn sine of nx over square root of pi. So these are the basis vectors for the orthonormal basis of L2 of negative pi to pi. So we can now compute these coefficients, and all you do is take the inner product with itself. So in other words, A0 is the inner product of f with 1 over square root of 2 pi. So that's the integral of x squared dx over square root of 2 pi from negative pi to pi. And then AK is the inner product of f with 1 over square root of pi cosine of kx. So that's the integral from negative pi to pi of x squared over square root of pi cosine of kx dx. And the last, oh, that's AK, sorry. So then the last coefficient is the inner product with that. And we get, let's see, this is the x squared over square root of pi sine of nx dx. Right, and you know, I can pull the 1 over square root of pi and 1 over square root of 2 pi out of the integral if I want. Well, so I thought, let's just use some mathematical software to do this. So what I'm going to do is going to use Sage Math. And so if you Google Sage Math, you can get to this, and then it will do symbolic calculations really easily for you. So I'm going to show you that. Make it kind of big. All right, so the first thing that's kind of weird you have to do is you have to tell it what variables you have. So I'm going to use x and n for everything. So I'm going to do that. And then I'm going to, my coefficient, I'm going to write a formula for it. So let's do the first one. So the first integral is 1 divided by square root. And it's pretty much, you just guess what you're supposed to do with Sage Math, and it usually works. But otherwise, you can Google, how do you blah, blah, blah in Sage Math, and then it'll show you how to do it. So, and then, let's see, I guess I want to do the integral of, okay, so this is the first one. I've pulled out the constant, so it's just the integral of x squared. And x is going from negative pi to pi. I think I have done this correctly. And if you want to actually show the answer, you can do this as you go. So I am now going to go down to evaluate. And let's see what we get. Yes, we got it. And let's see, so that would be, Huh. Okay. So this one is, I'm going to write it down on my formula there. Square root of 2 over 3 pi to the 5/2. So let's see. So when we multiply it times 1 over square root of 2 pi, the square root of 2's cancel. And then one of the pi's cancel, and you get pi squared over 3, which matches with that. Yay. So that's good. We got that one. All right, let's do the cosine one next. So now I'm just going to go back up to here and change my integral to times cosine of n times x. And it's just square root of pi this time. I'm dividing by. All right. So let's see what we get. Oh, it's probably already got it. And there we have that nasty formula. Wow. And, you know, this is the kind of thing where I'm sure it can simplify better. Like cosine pi n, that's the same thing as negative 1 to the n. And this one is just 0. Oh. So in fact, it's 4... Let's see. So let me rewrite that. So that's 4 times let's call it Bubba equals 4 times let's see, pi n times negative 1 to the n, because that's what cosine n pi is. And then that term is 0. And then I'm going to divide by square root of pi n cubed. Divided by square root of, oops, that was supposed to be a parentheses, pi times n cubed in the bottom. And then I'm going to show Bubba. Okay, so let's see what we got here. Okay, right. And now let's see if, and then why don't we want to see if that's actually the same, that we didn't make an algebraic mistake. So why don't we compute this for a couple of different n's. So let's, the difference between the twos. And then we want to substitute, so let me see, substitute n equals, I don't know, 11, and then maybe why don't we also do the same thing for like n equals 12, and then if those are both 0, we probably did it right, so let's just check. Okay, I think I did the right thing. Yep. So that's right. So it's 4 square root of pi negative 1 to the n over n squared is the formula. So I'm now going to write that down. And notice that if we multiply it times this, the square root of n's cancel, and you get negative 1 to the n times 4 over n squared, and boom, that's what we got. So what should we get for this one? Does anybody know? Nothing. That's right. We should get 0 for that one. Right. All right. So let's compute the sine integral, and so that'll be easy to check on Sage Math. So let's see. Go back to Sage Math. Why am I not finding? Oh, there it is. Okay. So actually, why don't I put just sine here, and everything else should be the same. Yeah, we'll just do that. Boom. All right. Yeah, I don't think, we didn't assume that n is an integer. There's a way to do that, and then it will compute it. But boom, guess what it got? 0. Wow. All right, that was quick. Excellent. So now we can go back to our calculation again. So this is 0. So therefore, summation of, well, the Fourier series. I actually should say Fourier series of this equals, because it's not actually equal at every point necessarily. And we actually plug it all in, and we actually get what we assume, because this one times 1 over square root of 2 pi is that, and then this one times 1 over square root of pi is 4 times negative 1 to the n over n squared cosine of nx. And I always like to just test these things and see if that's right. And so, by the way, that's the end of the problem. This is part A of the problem. And let's kind of look at it. Oops. All right. Let's go to Desmos. Okay. There we go. And there's x squared. And man, that's a pretty close fit. Let's only go to like 3 and see what we get. Oops. Still pretty darn close. Wow. Let's go to 20. Oh, but notice it only works between negative pi and pi. And that's the reason of that is because the Fourier series is always periodic, and it change. As if you add 2 pi, you're going to get the same thing. So, but it does very closely approximate, and you can actually see that it actually converges to the function everywhere. It's amazing. So anyway, let's go answer the rest of the questions on the exercise. So back to this. All right, so let's see, what is question B? So question B is, does it converge in L2? And the answer is yes. Fourier series always converges to an L2 function. Since that's the Rees-Fisher theorem. Yeah. And C is, does it converge pointwise? Does it converge uniformly? Well, it kind of looks like it does from the picture. Can we see why? Well, not real easily, but the answer is actually yes. The second thing implies the first, by the way. Because if it converges uniformly, then it's the partial sum is a continuous function, and the uniform limit of continuous functions is continuous. So then it would actually converge to a continuous function, and this is a continuous function. So therefore, since it converges in L2, it also has to converge pointwise. So whenever you get uniform convergence of a Fourier series, it does converge pointwise, if it's to a continuous function. And let's see. And then how can we actually see that? Well, look at the nth partial sum and the difference between the infinite sum and the nth sum, because that would tell us whether it converges uniformly. So let's call maybe Fourier n is the sum is pi squared over 3 plus sum from n equals 1 to n of for negative 1 to the little n over n squared cosine of nx. And then f infinity minus fn would be sum from n equals capital N plus 1 to infinity of 4 negative 1 to the n over n squared cosine of nx. Now, if we can bound this by something that is small, then we know that it converges uniformly to f infinity. So, well, it's actually fairly easily to do because we can bound this nicely because cosine's between negative 1 and 1. So observe that f infinity minus fn is less than or equal to sum from n equals n plus 1 to infinity of 4 times negative 1 to the n over n squared cosine of nx. And then that's less than or equal to, well, it's probably equal is what I had before, but it's the sum from little n equals capital N plus 1 to infinity of 4 over n squared. But by the p-series test, this series converges. So the tail of the 1 over n squared series, which is this, must go to 0. So for all epsilon greater than 0, there exists capital N such that summation n equals 1 to n plus 1 to infinity of 4 over n squared is less than epsilon. So therefore, this series converges uniformly. Notice the capital N does not depend on x. And so therefore, it's a uniform convergence. And so therefore, the answer must be a continuous function, and two continuous functions either are equal or they have their differences has a non-zero L2 norm in absolute value. Yeah. So there we go. So we answer that question. And then question D of that question is why are the sine and x coefficients all 0? And so remember, this is what the expression for the function is. Well, there is a reason for that. Why do you think there's no sine of nx coefficient in there?
Gee, that is odd.
That's exactly right. Because the sine x coefficients are odd functions. Odd function. X squared is an even function. So the integral x squared sine nx from negative pi to pi dx is going to be 0. So we actually didn't even have to calculate this. We could have just looked at it as an odd function. It's an interval that's symmetric about the origin. We got 0. So, great. Okay, so we have answered that question completely. So let's look at another exercise. So this is 4.1.4. So the exercise is, suppose that Fn is a sequence of functions in L2 of negative pi to pi. Consider the following statements. I, Fn converges pointwise. Two, Fn converges uniformly. And three, f of n converges in L2. So question A is, prove that 2 implies 1. Oh, I think I have to say that this is a sequence of continuous functions. Okay. All right, because otherwise this is false. All right, so here we go. So the proof is if Fn converges uniformly, then the limit is a continuous function. Since the uniform limit of continuous functions is continuous. And also the uniform convergence implies pointwise convergence. For any sequence of functions. So in other words, if you pick an x this is going to, if this converges uniformly, that implies that for specific x, the n can be chosen independent of x, but it doesn't matter. Okay. Well, given an epsilon. Yeah. So in fact, if n is greater than or equal to n, yeah. So it just is kind of an extra bonus you get pointwise when you talk about uniform convergence. So actually, no, we didn't need that it's continuous. So maybe not. All right, great. And then let's see, that was A, and then B, prove I does not imply two. Well, we just need to give an example of a sequence of functions that doesn't converge uniformly, but it does in L2. And I think you could probably make an example of, let me just rate an interval here, and then you could have something where the bump is like stays at 1, and this is like 1 over n, and then it slides that way, and then it converges in L2 to 0, and but it's yeah, it's actually supposed to be not, and it converges pointwise, but not uniformly. That's just one example, but you could probably think of a better one. You could just do a triangle, actually, make it really simple. From here to 1 over n or something, and then a height of 1. And then in L2, it can, because the area goes to 0, it would also converge to 0. And pointwise, it'll go to 0, but not uniformly, because you've got points that are distance 1 from 0, no matter what n is. So, and then let's see. The next question is, prove that. Let's see. Here's that 3. No, that 2 implies 3. So let's do the proof of that. Well, if it converges uniformly, so suppose Fn converges to F uniformly on negative pi to pi, then if we look at the L2 norm, we're supposed to show that it converges in L2. Let's look at the F minus Fn squared. And so that's the integral of F minus Fn from negative pi to pi. All right, well, we can make this less than epsilon. So for all epsilon greater than 0, there exists n in n such that for all little m greater than or equal to n, we have absolute value of Fn of x minus f of x is less than epsilon for all x in negative pi. That's what uniform convergence would mean. All right, so that implies that for all m greater than or equal to n, integral of f minus f, oh, I forgot to put squared, sorry. Squared equals the integral from negative pi to pi. And now I can put a less than or equal to, and then I can put epsilon squared there. And so that would be 2 pi epsilon squared. So therefore, since that goes to 0, since for all epsilon 1 greater than 0, if we let epsilon equal, let's see, square root of epsilon 1 over square root of 2 pi, then if we plug that in there, we will get epsilon, right? There exists n as above, such that for all m greater than or equal to n, f minus fn squared is less than epsilon. So therefore, you get convergence in L2. QED. Right, good. So uniform convergence implies both pointwise and L2 convergence. And then the last question is D, prove L2 convergence, which is the third one, does not imply pointwise convergence. Well, actually, same example as B. Oh, wait. No, because it does converge pointwise. Okay, never mind. So we need an example where L2 convergence doesn't imply pointwise convergence. Oh, well, just how about this? Have it just be 1 at 0 and then 0 everywhere else, just independent of n, and then f of x equals 0. So fn converges to f in L2, since the integral of fn minus f squared equals 0, because it's only non-zero at one point, and then but fn does not converge to f pointwise, since fn of 0 equals 1, f of 0 equals 0. Okay, so that's a good example. Well, so we took care of that stuff.